We have studied the molecular orbital diagrams for the simplest of the molecules, and we have seen that for hydrogen 2 you have the sigma 1s bonding, sigma 1s anti-bonding, and for molecules such as lithium 2 or the one that does not exist, beryllium 2, you have, well, still the sigma 1s, the sigma 1s anti-bonding, and now you have the sigma 2s bonding and the sigma 2s anti-bonding. As you may predict now, what may be interesting is to start mixing p orbitals, because these molecules so far only contain s orbitals. So when you mix two s orbitals, you obtain either the anti-bonding or the bonding kind of, this looks like a monster. Uh, this would be the anti-bonding and this would be the bonding, in which there is a constructive interference of bonds in between. Alright, so the shape of molecular orbitals for s, when s atomic orbitals are combined, it may seem straightforward. Let's look at what shape may give when atomic p orbitals combine to give pi molecular orbitals. When the p orbitals are not in the axis of the bond, they may give this pi bond, this pi 2p, right? And this would be the distance, because there is no electron density between the atoms. This is why we call this a pi bonding. And if these two waves combine in a destructive manner, this is the pi anti-bonding, in which there is no electron density between the atoms combining. Notice that if you combine two p's, but those two p's are on the axis of the molecule, it will not form a pi bond, even though you're combining p bonds, p atomic orbitals. You will still form a sigma to p, because what sigma and pi mean is whether there is electron density along the axis of the molecule. So the sigma 2p will look something like that, with these tails in the back that do not participate in the bond, and the anti-bonding 2p will look like that, in which the tails are larger and therefore the electrons are not found between the atoms combining. So let's look at the molecular orbital diagram that takes place when we mix p atomic orbitals. So let's see. One must distinguish two different cases. In boron, carbon, and nitrogen, the order of these two atomic orbitals are exchanged with respect to in oxygen, fluorine, and neon. The rationale behind is what we call the 2s, 2pz mixing. We will not go much farther, but in this case there is mixing, which means that these two kind of combine with each other and form a new combination, such that the anti-bonding here becomes more stable and the bonding here becomes more unstable. This is not as important to understand as it is to just realize that the molecular orbital diagram for the boron, carbon, nitrogen, the first half of the p block, is different than the molecular orbital diagram for oxygen, fluorine, and neon. If you do not quite understand the mixing, we will not spend too much time explaining it here. Make sure you talk to one of us so that we can explain this a little bit farther. The whole idea is that waves can keep combining with each other if they are close in energy and shape, so you may see some of these anomalies from the natural sequence of molecular orbitals that you would see. So let's see what is happening when you have, for example, boron 2. When you have boron 2, notice that you will have, so you have 1s2, each boron, 2s2, 2p1. Something that you may notice is that in this diagram we did not draw the 1s. The 1s would be down here. There would be the 1s. However, as I'm writing here, from now on we will avoid drawing the inner full shell molecular orbitals because they contribute 0 to the bonding, because if by definition if they are full shell they will have as many orbitals in the bonding than the anti-bonding, and they will therefore cancel each other out in terms of contributing to the bond order. So let's try to calculate the bond order for boron. As we said, these two will be ignored, so you have 3 valence electrons that need to be 3 from each of the borons. So in total you have 3 times 2 borons, you have 6 electrons to place in here. You have 1, 2, 3, 4, 5 and 6. So therefore we can predict that boron 2, even if you were to draw the Lewis structure, boron 2 has unpaired electrons, and the HOMO is this pi 2p, and the LUMO is this sigma 2p. Okay, this will lead to specific reactivity that we will not talk too much about now. Okay, but at least hopefully you get the whole strategy correct. Here you identify the number of electrons or valence electrons, then once you're given the molecular orbital diagram, you can fill up the orbitals with electrons. So let me just finish this video. You will practice more in class, but let me finish this video by answering these questions. So based on molecular orbital theory, in order to weaken, we want to weaken the nitrogen-nitrogen bond in N2, what should we do to electrons? Should we add electrons, remove electrons? To do that, we must remember that bond order is related to the strength of the bond. The higher the bond order, the stronger the bond is. Notice that in this diagram there is mixing. So the pi is below the sigma, which is the same that you see here. Okay. Again, you will be given all these diagrams. You do not need to memorize them, but at least you have to understand, or at least have heard about this 2s 2p mixing. So now let's try to answer the question by first figuring out what is the bond order of the molecule N2. N2, so how many valence electrons does each nitrogen bring? You have a 2s 2p3, so that is 5 electrons each nitrogen multiplied by 2. You have 10 electrons to place in this molecular orbital diagram. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Bond order in this case will be, well, I have how many in the bonding? These are all bonding, so I have 1, 2, 3, 4, 5, 6, 7, 8 minus these, that is 2 divided by 2. The molecule of nitrogen neutral has a bond order of 3. What happens if we add an electron? If we add an electron, that is for N2 negative, we would need to place 11 electrons. The bond order would need to be such that if you place an extra electron here, this will be 8 minus 3 divided by 2. This is 2.5. So we have weakened the bond by adding an electron. What happens if you remove an electron? Now you have 9 electrons. That is, let me remove it. Okay, so in this case you have the bond order, instead of 8, now it's 7 minus 2 divided by 2 again is 2.5. So nitrogen or dinitrogen will have a weaker bond regardless if you add an electron or remove the electron. Okay, so either by adding an electron or removing the electron, the bond will weaken. So this is one of the more powerful predictions that molecular orbital can tell you.